Hello and welcome to this part two of lecture one. I wanted to record also some kind of like a small introduction where I tell you a little bit what I think differential equations are, and also some of the most important differential equations that you would be studying in this class. I will be discussing those and kind of showing you how we use those. And then I would like to tell you as well a little bit about the differential equations I love. So essentially, write three small units as a way of introduction. I will tell you what differential equations are, what are the important differential equations for Math 2 to 3, the ones that you should absolutely know how to do by hand, right? Those ones, well, essentially, you have to do those ones because they epitomize or they represent some kind of other, basic general approach to differential equations. The other reason why you should train on those equations by hand is because the kind of analytical skills that you will learn will help you in actual real math problems, right, later on. However, they are super easy to solve in a computer, and I hope today we can, in fact, in this like long form recording, and you should expect, every lecture to be between 1 and 3 hours, right? So this is a masterclass lecture in which I try to tell you everything I kind of know about this to the extent it's possible to do it in, 14 hours or something, which is, the amount of time I will be recording these classes. So a small recording today, just this little bit. So let me find my bearings here and let's scroll down here and see whether I can tell you a little bit about this, what differential equations are. So let me put it in here. I have, my setup is still, I haven't taught, you know, record so much since the beginning. So what are differential equations? So they are relations between, or equations that relate an unknown function with their derivative, right? So essentially these are mathematical relations, mathematical equations involving an unknown function and its derivative. The simplest example of differential equation, which is one of the ones that you should absolutely be able to do by hand, right? I believe that to the extent that if you are not able to do the exponential growth by hand, you shouldn't pass the class, right? So you better know how to do exponential growth by hand because if, and understand what exponential growth is. In fact, if you follow the textbook, very early on, they will tell you, right, which ones are the important differential equations and how to more or less start to think about them. Unit 1 is going to be very helpful for that, and the beginning of Unit 2 is also pretty helpful for this. But differential equations are going to be mathematical equations involving an unknown function and its derivatives, right? So an example of this would be the exponential growth equation, which we will discuss in detail soon, at some point. But essentially what the exponential growth equation means is that you have some unknown function n of t. This is called the dependent variable. And this t is called the independent variable. So, you have this unknown function. Typically, what helps is actually to interpret this. So, for instance, n typically would be maybe a bacterial population. Can be, BTC, BTC price during a bubble. right? And then the t could be time, right? So in that exponential growth equation, if I write it here, maybe in this little corner that I have here, that exponential growth equation is something like this, look. And you can see that there is, what this is telling you is, okay, the derivative of this function is the function itself multiplied by k, right? So, if you have 2, n equals 2, the derivative would be 2k. But if you have n equals 4, the derivative would be, 4k. So the derivative is proportional to n. So the rate of change is proportional to n. Now this differential equation, we can classify it. You can look at the order of the derivative, and this is a first order derivative. So this differential equation is a first order differential equation. Now, if you look at the equation itself, the only dependence on the t, which is the independent variable, is on this derivative, right? So in fact, if you think about this as a, dynamical variable, you will see that it only depends on n prime, the derivative of n and n, but not on t explicitly. So this equation is called also an autonomous differential equation. So it's a first order autonomous. Also, you can see that the n, which is the known function, appears all by itself. So it doesn't, you don't have n squared, you don't have log n, you don't have sine of n, it's just n, right? So those equations, we call them linear. So it's a linear first order autonomous ordinary differential equation. And you have this n here. You can see that when you want to solve for n, right, you have to undo the derivative, right? That means that you're gonna have to do an antiderivative. And if you do the antiderivative, it means that you're gonna introduce an integration constant. So, if you solve for n, this equation as it is, you're gonna get an integration constant. Today is maybe not the day to do this because we have entire lecture on exponential growth and logistic growth. So we are gonna cover this in detail. But this is an example of a differential equation. Now, because you have to do that and, one antiderivative to cancel out this derivative and solve for n somehow, right? You also need to fix one integration constant. If the equation had been second order, right, you would have needed two integration constants. So I think the general solution of this equation here is gonna be something like this. In fact, we have to supplement the equation with some initial condition, right? There will be some initial value of n of t at t equals 0. There will be some initial value, and that initial value is n naught, right? So this is called initial condition. Probably I'm writing on top of my face now. Good. Initial condition. And this is the actual equation, which we are saying is a first order separable, homogeneous, linear, exponential growth. Okay. If you integrate this, then the solution you're gonna get is gonna be this. Depending on the value of k, if k is positive, this would be exponentially growing number of bacteria, exponentially growing Bitcoin price as a function of time, it will grow exponentially. The higher the k, the faster it grows, right? If we are to graph this function, right? Let me go here and graph it here. There is some initial value at t equals 0, so here is going to be t, and here is going to be n of t. There is an electrical storm. I bet the electricity is going to go out. I hope I don't crash everything. And the recording too. Ooh. So this is a node. right? So at t equals 0, so if k is negative, it's gonna decay, right? And at t equals 1 over k, right? It's gonna be n naught over e. That provided minus k. That's for k negative. For k positive is gonna be the opposite. Let's put a different color. Let's see if the blue works. Maybe the blue works. Let's see. Yes, it works. So for k positive is gonna be something like this. So in one case you have growth and decay. What is important here is to look at the slopes here, right? At a node, the slope will be whatever it is, right? But if you go twice, right? Twice here, right? 2 and node, then you can see that the slope will be k times the one at n node. The slope here will be k times, yeah, k times the slope here. So if you, sorry for the cough. So if you graph, right, all of that, you can see that at an individual value of n, right, the slopes of any solution for any value of n naught, right, it's gonna have all the slopes like this, right? They are gonna be equal to each other. These are called slope fields, and I will tell you how to construct them in the next lecture. So if you go at n equals 1/2, right, it's gonna be something like this. So that's for k negative, right? No, for k positive, right? So it's gonna be smaller. And for k equals 0, of course, it's gonna be, the differential equation is the slope is k times n. So if you put n equals 0, then you get 0 slope everywhere. Right, and so on and so forth, right? So there are this stuff in here, it's like twice, so it's probably here, it's gonna be something like this. So these are called slope fields. You should learn how to build them by hand, just by consideration, certainly for the exponential growth and for the logistic growth. So that is one thing that I wanted to tell you about what a differential equation is. And you can see that it's always going to be the same thing, right? It's going to be a relationship between a function and non-function, in this case n, and the derivatives in general of that function, right? There is another thing that you should know, probably, is the general form of a differential equation, right? The differential equations, they all have the same general form. So the general form of the differential equation is going to be a relationship, a functional relationship between a function and its derivatives. So it's going to be something like a big function f that is going to be relating a function and its derivatives. Let's say that y is the dependent variable and x is the independent variable in this case. So here we will have a function, let's say n derivatives, so there will be the nth derivative of y with respect to x, the nth minus 1 derivative of y with respect to x n minus 1 times, the second derivative of y with respect to x twice, the first derivative of y with respect to x, y, and x. And that is going to be equal to 0. You might not believe me, right? But for instance, take an example. Exponential growth example is n prime equals kn. Rewrite as n prime minus kn equals 0, and then you have your function f is gonna be n prime minus kn, right? So that's the general form of a differential equation. Whatever example that you want is gonna fit into this particular one form here. So that's the general form of a differential equation. Whatever differential equation you form is going to involve a relationship, a functional relationship between a function and non-function y, its derivatives with respect to the independent variable x in this case. And y and x you will have to interpret depending on the problem. Y could be a population growth, could be the speed of a particle, could be the pitch angle of a plane, could be the bending, the displacement on a wing under stress or load, even aerodynamic load. Could be the magnetic moment of a particle as a function of time. Right, there are so many things that you can think about, but whatever it is, it's gonna fall into this form, general form. And what you will be studying by hand are the simplest examples of this particular one form, right, of this general form. The most really simple examples. In fact, those are the only examples that you can have a chance of solving by hand. The great, immense majority of differential equations cannot be solved by hand, right? In fact, all of the differential equations that are being solved today, the hundreds of millions of the billions and trillions of differential equations being solved at this very moment, right? All of those are being done numerically by computer methods, right? That doesn't mean that you don't need to understand the theory of differential equations, right? And you are beginning to understand the theory of differential equations now, right? You already know one thing. These are mathematical relations between a non-function in these derivatives. Typically, they are going to be cast into some mathematical form, some general function, capital F, right, that we call capital F, is a general function of the derivatives and with respect to the independent variable, the function itself and the independent variable. So any differential equation will fall into this category. The other thing that you have learned, right, already into this small discussion, is this stuff in here, right? If I undo this derivative, I'm gonna have to pay the price, and the price is introducing an arbitrary constant of integration, because I have to take an antiderivative to cancel out this stuff and free the n somehow, right? And I will guide you how that is done. Essentially, it's done by a method called separation of variables, right? So dn over n is k dt, so then you integrate over n, you get natural log of n equals kt, you exponentiate that, and then you get natural log of n equals the kt plus constant, right? So e to the constant is n naught, and e to the kt is, yeah. So that's how we are gonna solve it. But essentially, the idea remains. First order differential equation, you will need one initial condition. If this equation were second order differential equation, you would need two initial conditions or two boundary conditions, right? You need to fix two integration constants. And that's already something like super important, right? If you understand that, you already have climbed a little bit the ladder of knowledge into the theory of differential equations. You know that a differential equation has an unknown function. There are derivatives of that. You have to develop methods to actually free the function from inside the derivative in a way that is mathematically consistent and logically true, right? So you get correct answers to your solution. But if this equation were of second order, then I would have needed two initial conditions. Third order, I would have to undo three derivatives, three constants of integration, three initial conditions. 20th order, so on and so forth. If you understand that, you already have a lot, right? So you know what differential equations are, what differential equations are. So what are the important differential equations in Math 223? So let me just see how this looks. Oh, wow, I'm running out of space. This is like problematic. But yeah, maybe I can do it in here. Like that. And then make a smaller pencil. So what are the important differential equations in Math 223? Let me maybe make a smaller, make it smaller. So, you will have to zoom in quite a lot. And I'm gonna change the pencil as well. to this pencil to read this, but I will post the, well, you have the recording. I will post also the, I will post also everything, right? So the lecture notes will be posted as well. So, well, number one, exponential growth. So this will be n prime of t. Well, we can put n prime equals kn with the initial condition n of 0 equals to n naught, whatever n naught is, right? So how to understand that? Maybe, n naught could be 3.5. So, the other thing that you can see here is that this is what is called the growth parameter. And that's another thing that you can learn now. Differential equations, including the ones we're going to be studying here, they have parameters. And as you change those parameters, like k, if k is positive, growth, k negative, decay, right? The dynamics can change in some way, right? So one thing that you should get an expertise, particularly in today that we have these computers available, right, is on studying the parametric dependence of your equations and understanding what happens when k changes in that equation. Not only what happens when k is equal to 1 or negative 3, as a function of k that you visualize, right? What about the logistic equation growth? Now I have to think very hard to remember this. It would be something like this. Let me write the name. So it's gonna be something like this. But then I think we have something like this. And critical, let's call it critical, or carrying capacity. So in this case, we have two parameters. We have k, that is this called initial growth. Jesus, electrical stop. Oh, it's just right there. It's just right there, but just in there. Well, let's hope for the best. Well, in any case, a growth parameter, and then here, NC, that's called the carrying capacity. Now, in ecology, this is important because this is the maximum sustainable population. So that is a very cool equation. It has two parameters, k and n. Depending on those two parameters, things will change, right? And again, it's a first order, so you are gonna need also n of 0 equals to n naught, some initial thing. The unknown here is again n of t, and the independent variable is t. Typically, this will be some population, typically an ecological population, and t would be time. So that's the logistic equation. And in fact, I could now go and show you in the Wolfram Cloud how to solve a logistic example. So let's see if I can do this. I need to be careful. I don't want to show you something embarrassing, but let's see if I can do it. Let's see. So if I go here and maybe this one? Yes, I can see that. So now okay, good. So now we have that window. I think it should be this window. If I go here to Wolfram Cloud, yeah, there it is. Sign in into Wolfram Cloud. So I'm gonna sign in with my Mongo account. I already created my basic account, right? And open a new notebook. Typically, I will show you how to do it. I myself, I have very bad eyesight, so I put it like this. And let's see if I probably would do better if I show the entire screen. Let's see. Yeah, like that. And maybe, just decreasing it slightly and moving it. And let's show a little bit more. I'm sorry, I have still to fix things. And now the problem is I'm in the middle of the screen. Exactly what I'm going to be writing. So maybe if I put it a little bit. This is like so complicated. Oh, I'm sorry, I apologize for these mistakes. So let me place myself in here. But then, yeah, let me place myself in here. I think I can do it like this. Look, I apologize for these mistakes. It's so bad. I think I will do it like this. Let's see if I can. Yeah, oh yeah, I will do it like this. I'm still like learning how to do this. It's easier than it seems, but you know. So I'm gonna start writing this solve value, this equation. And you can see if you click in the little I, and you, in the corner over there, and maybe I can place myself like entirely in the middle. In this corner here, right, it will appear some instructions, right? Details and options, examples, right? A bunch of examples. So you can already get it, right? You can already get an example. So that's pretty cool. Here is the scope, basic uses, boom, some example, how to do it. Particular solution, general solution. That's something that you are gonna need to do. What we want to do is to do the logistic differential equation. I wonder if I can define the equation like this. Equation is gonna be, oof, I don't know. This is gonna be improvised, so I'm gonna put it in the way I know how to do it. So I'm gonna type here the equation, and I'm gonna type just the equation first. So it's gonna be n of t, n prime of t, so the derivative of n of t. And you can see that the function notation, right, if you look carefully over there, I have to place myself properly, if you look carefully in here, the function notation has these square brackets. So the syntax has to be precise. So if you see that D is in capital, well, you have to put it in capital. It cannot be like this, right? It cannot be like whatever you want. It has to follow a strict rule. Now this is K times N of T. And if you recall the logistic equation, then that's multiplied by 1 minus N of T divided by N naught. And that's the logistic equation. And then I have to put the example is here, that's the example that is here. So you have to put the independent variable, so it's n of t, and the independent variable, x, in this case, t in my case. So I can get rid of this now. And now it's gonna give me the general solution of the differential equation with the constants of integration. And you can see that n naught and k, but there is this constant of integration c1 that appears here in the exponent, right? Now let's see what happens if I, rather than inputting just the equation itself. So by the way, you have to press shift and enter. So I'm holding down the shift key and the enter key then. So I do that, and you can see then it says input 2 and then output 2. I hope that you can see that in here. Yeah, input 2, output 2, and here is the complicated function. Not so complicated, in fact, right? So now we can do something else. We can put a symbolic. So this is what we call a symbolic solver. So by the way, notice the two equal signs in the equation. That means conditional equality. It means that that equality is only satisfied by the solution of the equation that you are trying to solve. So it's telling you that the equality is going to be conditionally satisfied by your solution. So in this case, I'm going to put n of 0 equal, again, n naught. Right? Oh, that is not what I was expecting. An initial condition. Oh, yeah, no, it's correct. This is only giving me n naught as a solution. How can that be? So if I put Yeah, I don't know. This is not doesn't sound correct. And I'm checking the yeah, should be correct. What about if I put a one? Now it looks better. Now it looks correct, right? Yeah, yeah. So you can see now that yeah, but it is a problem because this is a node, right? Oh, this is not a node. This is NC, the carrying capacity. Ah, and that's why I was having problems. This is N node. So if I put it right, okay, now it looks correct. So you can see, right, that the original equation, and particularly if we go back to the Krita screen, right, and delete this. And I actually deleted myself. No, where am I? Oh, here. Oh, damn. I deleted myself. How can I? Where am I? This is fantastic. Video capture. Oh, here I am. Fantastic. I just deleted myself by mistake. So if we look back here, right, that's the logistic equation. And you can see if I move myself into the thing that we have two parameters, K and the current capacity, and some initial condition and node. So in reality, there are three parameters, N node, K, and the current capacity. So you can see how quickly I was able to solve and get a formula, a general formula for the solution of that equation. So let me again show it. Oh, I have to be careful here. So again, this is the general formula, but if you substitute by numbers, right, and put some numbers in, like for instance, let's say that k is 3, let's say that k is 500,000, and that NC, right, the current capacity is 1 million, right? And then if we do that, the initial condition, let's say that is 10, boom. But in fact, I can put n not equals 10. That's more general, right? So then in that way, you just change n not at the beginning of your code. And then you can see, so you are fixing n not to 10, k to 500, nc to 1000. And here is the equation. So I'm gonna call that sol, my sol. So sol should be this function, let's see, sol of 1. If I do this, does it work? No. So probably I should do sol of t, like this. Yes, like that. And it doesn't allow me. So how do they, so I have to look into the, you see, sol. So why is stack times in here protected? So if I do sol, now I want to evaluate my solution. And if I do, I don't know, my sol of t. So that's how did you declare a variable equals sol? That works? Yeah, that works, but somehow I cannot do it here, somehow. So I will have to do it here. Let's call it pop of t, because it's a population. Let's call it, that is the solution. So now it has solved it. If I put a semicolon, what it means it cancels the output. You can see it here. If I find here some space where the cursor goes horizontal, then you can put in here whatever you want. But now I can, for instance, put a plot, sol of t, and then t from 0 to 10. Let's see what that gives us. Oh, it doesn't even show. Ah, no, because we call it pop, not sol. Ooh, that's too much time. So maybe 1. Ooh, maybe 0.1. So it's reaching carrying capacity very quickly. Oh, now we are seeing maybe 0.05. And now we can see the entire capacity. You can see that end node initially was 10, so axis labels. I guess if I put here n node, n of t, and then t. Oh yeah, good. It's not very good, this plotter. You can see the t is here, a very small t. I don't know. Yeah. So here we have the population here t. And maybe I can take a screenshot and just place it into here. So let's go here. Screenshot, snipping tool, new, and graphic there. So maybe something like this is enough. Again, remember that I want you to go through these notes and see how, you know, reproduce this stuff. Let's see. Oh, that's a new one. Why? Oh, because it's probably, yes. So this is not looking very good. Let me just like, again, try to resize it. Maybe a little bit like this. Yeah, and a little bit like this. So now if I go and zoom in a little bit more and just find my space here, like that. So essentially, right, if I rewrite our equation, let me rewrite it in here for your viewing pleasure. So this would be something like n prime equals to kn times 1 minus n divided by the carrying capacity. And this stuff here, this limiting value at t equals infinity, that is the carrying capacity. That initial value, that is the n naught that we fixed at the beginning with the initial condition. And then at the beginning you have an exponential growth curve, approximately exponential growth. But then about here, it's kind of like slowing down, and this is the typical, it's called a sigmoid function, or a logistic growth function. So here, you know, when we start with n naught is less than the current capacity. And that it increases to the current capacity because, you know, there is like available food or something, so they reproduce to the limit they are able to. Let's see what happens if we start with an initial condition, right, where the end node is actually larger than the current capacity. Let's put it 1100, right? Now here the k, that's why it didn't work. The k is so huge, right, that, you know, it just goes so quickly. That's why the time scale is so small. But if we keep it like this, right, and I reproduce, now it's gonna be very different. Ah, you see? Now it started, so let's put a plot range all. So now you can see, I don't know if you can see it very well, but if you look carefully, you will see, oh, you know, I forgot to share my code. Darn, it's so difficult to do these things, right? Oof. But I just have done the calculation with this other starting point. Let me show you. So here is the same, but in this case, n naught is actually larger than nc. nc is here now, equals to 1000. So essentially you start with more population that you can sustain, and then it decays exponential to the current capacity. So if I just graph it on top of the other one, if I had started, right, with a value of n naught higher, somewhere here, let me put it maybe in red. or maybe in this magenta, then essentially, right, that will have like fallen down to, from the top, right? So if you have less than the current population, less than you can carry, the population grows. If you have more than you can carry, the population decreases. That also applies, for instance, for jobs, right? In jobs, right, there might be that you have, not enough engineers, right? So then, the number of engineers here, the demand is here, the number of engineers, people are gonna, engineers from other places are gonna start applying because you are asking for engineers, so they are gonna increase it. Imagine that you have too many engineers, right? So then people are gonna lose their jobs until you reach the optimal number of engineers that can be sustained at that time. Incidentally, that's why you have to maximize your GPA, right? It sucks to maximize your GPA, but yeah, you have to do it. You have to do it in a legit way, right? You have to maximize your GPA by maximizing your mastering of the skills that you learn in the classroom. Because in a competitive environment, right? The ones that go here are not the best ones, right? The ones that go down here, these ones that are gonna lose their job, these are not the best ones, right? The best ones are gonna be kept, right? If there is a demand, right? Maybe you don't have to be very good and you will get a very nice job, right? But if there is not a demand, there is an over, you know, then you have to be to survive in the field. You will have to be good, and that means you will have to know all this stuff inside out, right? So you don't want to be, I don't know, you know carried by the wind of geopolitics, or we are all being carried by that wind, the wind of finance and geopolitics and different financial situations, or market stability situations. We are all carried by those, right? And they are beyond our control. Now, within these kind of variations will happen within your lifetime. So essentially, when I started my PhD, there was a shortage of PhDs in my country, but there was no funding. So in England, there was a lot of funding and a shortage of PhDs. So, you know, I could have done my PhD in my own country, but there was no funding, right? So I went to the with the English, right? I did a PhD with the English, and they had the funding. So you are here. In my country, it was more like here, right? I couldn't, right? If I had started, yeah, it would have been very difficult to for a PhD, right? Other jobs maybe not so difficult. So what a long lecture I have been recording for such a long time. There are a few more that I want to tell you about. Another super important one is the so-called harmonic oscillator equation. The harmonic oscillator equation is great because it really summarizes, a lot of physics. Plus mu x prime. Some people put a 2 here, plus omega naught x. I don't like doing that, equals 0. Now x of t is called the displacement from the equilibrium position. And this would be the acceleration. Well, this would be the force, right? Mass times acceleration. X prime would be the velocity. And x2 prime would be the acceleration. Now, this equation is so important because all linear homogeneous equations, can be solved using the same methods. So if you know how to do this one, essentially it's the same, gonna be essentially the same thing for third order, fourth order, whatever linear equation. And in fact, right, the fastest route is always to solve it by computer, but this is one of the ones that you can really, from beginning to end, solve, right? You must absolutely solve this equation by hand in a general way, right? The way to solve it in the end is very nice. You transform that equation, that differential equation for x, second order, there will be two integration constants. There will be two constants of integration. Your general solution will have A and B, right? Two unknown constants. You will need two initial conditions, so I'm gonna put those in for you. One would be the initial position, and one would be the initial velocity. In all Newtonian mechanics, initial position, initial velocity. You can also do position at time t1, position at time t2, or velocity at time t1, velocity at time t2. But I think velocity at time t1, velocity at time t2, I don't know that you will get the position entirely. I think that you probably won't. So probably you will need an initial condition for X and an initial condition for B. I have to think about it. I haven't thought about it too much or enough to have it fresh in my brain. So that one is super important and you must absolutely know that one. Of course, the other one that you should know is the force harmonic oscillator. So that will be the same equation, but with a forcing term on the right hand side, something like this. That you will learn to do it. I will teach you how to do it by Laplace transforms. In the homeworks, you will learn how to do it by methods like separation, variation of parameters, or undetermined coefficients. But I will not lecture about these methods myself. You have recordings that you can. Finally, the other one that we can say that is going to be very important for you is going to be systems of linear equations. This would be systems like this, particularly this one. The first order 2x2 system. So with initial conditions, so that will be that. Now, what are my favorites? So I think those are the three, the four equations that, every single, differential equations student should know. Exponential growth, logistic growth, harmonic oscillator, force harmonic oscillator, linear systems, particularly the 2x2 linear systems, plus the series solutions in all the cases for all of them. That's by hand solutions, but then there is the entire theory of differential equations. That's a different thing. For instance, you might say that a first order differential equation, the solutions form a vector space, which is one dimensional. So solutions of first order differential equations are vectors in one dimension, right? Solutions of a second order differential equations, two constants of integration, right? Those are like coefficients of a vector, right? So this would be, or components of a vector. This would be a second order is a two-dimensional vector space, right? The solutions can be sine plus cosine, or it could be sine times exponential. There is some rules on how to build those spaces. That is two first order equations, two constants of integrations, two-dimensional space. In a way, the system is equivalent to a second order system because there are two initial conditions, just like that, which answers my previous question, right? You can specify the velocity at 2 points, I believe. Oof. Certainly you can do it with the position. Yes, so yeah, in this case, right. No, because this would be a position and this will be a velocity. So these are the ones. So what are my favorite differential equations? So some of them are here already. One of them would certainly be the harmonic oscillator equation. Most important equation that you can really find in physics. It doesn't get much more important than like that because everything around us is gonna be oscillating. Atoms, electrons in atoms, they have like, some kind of trajectory type of thing, probabilistic trajectory. So, those, they bounce back and forth too, right? Planets among the stars, They're kind of, they're doing these circular orbits, but along Y they are doing like this, and along X they are doing like that. So they are oscillators too. There are so many problems that can be, addressed with this bit. Of course, I would say the same thing about the logistic equation, particularly the exponential growth equation, which is a particular case of the logistic equation where the current capacity is infinity. So, the sigmoid curve keeps growing forever, right? It's kind of delaying, where this like leveling off is gonna happen, right? So you can delay it forever, and then you have exponential growth. Those are all very important. Now, some of the equations I like the most, I would describe them as partial differential equations. So probably I can go to GeoGebra and show you, maybe to GeoGebra, to, oh God, I'm kind of like canceling the wrong one. Which one is this? This one, and now this one. Okay, so rather than showing you there the Wolfram cloud, I will go here and put a maybe Schrödinger equation. A Schrödinger and cat? No, equation, no. The Schrödinger equation, look, it has like this shape there, right? That is a kind of matrix form of the equation. So H is essentially a matrix and psi is essentially a vector. That's called an eigenvalue equation, and you will meet them once you study systems of equations. But if we go here, right, we can see it probably in its full form. So this would be like this one here is a partial differential equation. You have the solution psi, the unknown function. It's a function of two variables. So the derivatives have to be partial derivatives. And you have two independent variables, which are x and t, and one dependent variable, which is psi. Now again, super important in differential equations, know the interpretation of your solutions. Logistic growth, we were doing in logistic growth, we were doing populations, right? Here is probability amplitude, right? A complex probability amplitude. The modulus square of that is what we call a probability density or a probability distribution, right? So this will tell you the probability distribution of finding the particle at position x at time t. And it has the shape of a kind of wave. In fact, it's some kind of wave equation that tells you that, material particles, electrons, neutrons, this kind of particles, they behave as waves. And there is a differential equation, which incidentally is very closely related to the harmonic oscillator equation that is in here. The harmonic oscillator equation, in a way, is a wave equation. So the Schrödinger equation, I like the many bodies Schrödinger equation. Boom. Let's say there's some images here that we can show. Schrödinger equation. Okay, right. This is not very good because it's not showing the equation. So here, there is an equation. Let's see this. What they say? Slide player. It's gonna have like weird commercials. This is like so bad. It's gonna make me pay. I shouldn't have clicked on there. Are you seeing this? Yes. Okay, here. Wow. Is this a legit universe review? Let's watch the universe review. Wow, this is so bad. Let's go here. Okay, here. Wow, this is like the worst. No, I'm not gonna do this. Maybe I can just like copy it and paste it into my thingy. It doesn't look good, It doesn't look good. Let's go, you know what? Let's ask a chat GPT for, you know, we can find one. Maybe in Wikipedia. Where is it? Here. Let's go here. The formula, man. Okay. So this would be, right. Wow, it's only showing you the Hamiltonian, right? It's kind of like difficult. But There is this, this is for a two electron atom, the helium atom, the second simplest atom, right? So you have like a second derivative at a three-dimensional second derivative known as Laplacian, and you have the positions, right? These are derivatives with respect to x, y, and z, but there are two sets of x, y, and z. The x, y, and z of electron 1 and the x, y, and z of electron 2. Those nablas in there are those. And that's the kinetic energy. And that's the potential energy that, it has like R1, R2, and then the interaction term between electron 1 and electron 2. So that is super complicated, right? Because there are two sets of variables, right? Yeah, very difficult equation. Another one equation that I like a lot is the Poisson equation. This I made a living out of this equation for a long time here, that one. So if you have like a charge density F, the electrostatic potential will be phi, if you are able to solve for phi. But it is easy to solve because here you have the full solution written in integral form. Now, this stuff is almost unusable, particularly if your system is extended. If your volume of integration with the entire space, you are doomed, right? If your f of r, that charge density is kind of like everywhere, you are doomed with this. You have to do some trickery. This is one of the tragedies of my research career. I found out a trickery from a very long time ago to actually solve this for the general case. But when I wrote the paper, this was a detail in my paper, but it was the most important thing of the paper. I just didn't realize the importance of it. So then later on, other people did, like that. So those are examples, a few examples of the differential equations I love. Talking about love, there is also mathematical models of love. Mathematical lovers of love. Oh, look. Um, let's say ResearchGate. Yeah, so difficult to verify this. Look, 2011. Let's see what he's doing. Oh, oh, by the way, look, you're so lucky. You can get to see the merge report of, of all my courses. Which is good that you see it. Let's see. Where is it? Oh, I'm not sharing. Yeah, darn. So I will have to share a different screen. This is not good. You can see there is a bunch of them. Let's see. Open the PDF in the browser. Modern Education in Computer Science, 2012. This is not a very famous journal. But Gmail addresses, but maybe it's because I don't have an email address, a proper email address. I wouldn't be surprised. Or maybe it doesn't work very well, right? So people, people actually can do super serious research, and I know this for a fact, coming from places where maybe they don't have like the best gear. So I wouldn't discount, although the journal maybe is not very good. I wouldn't discount this because of Gmail addresses. So I think, let's see. Human behavior is a combination of several feelings. These are two cases where a person likes other individual or not. Liking of an individual leads to love and finally happiness. Hopefully. The feelings of love may be different from forms, maybe in different forms, but here considered to be partner's love. It's not very well written either, but maybe English is not there. Wow, it's interesting. Romeo and Juliet is the creation of Taj Mahal. Wow, that's super interesting. Actually, like in the paper. Guess what the model is? Linear systems of equations, right? So let's see what they say. So the papers are by Rinaldi and by a number of other people. So yes, Sprott, also one. So Sprott's model is there. Is this model linear system, right? The feelings of Romeo for Juliet, the feelings of Juliet for Romeo, and then you know the the rate of change of those emotions depends on the current state of those emotions, both for Romeo himself and for Juliet. So his perception of Juliet's feelings influence his current, rate of change of the feelings. Right. So you can see people talking about differential equations I love, right? Well, the differential equations that describe love, are one example of differential equations that I love. So long recording in the end, but I hope it was fun, worth of your time, at least to get some insight of the kind of things that we will be doing this semester. So work hard, study. You should absolutely complete unit 1s, 2, and 3 by week 2. So you have plenty of time, but do it. Do it because unit 1 is very simple. Unit 2 and 3, there is a lot of labor to be done there. Remember, you need 3 problems from every subunit to be in your notebook, plus lecture notes from my lecture notes. From this one, you don't need to take so many, and I will put the Blackboard up in case you want it. Yeah, other than that, I hope you enjoy it. Thank you so much. Ciao.